Hello, everyone. Welcome to this talk. I'll be talking about fraud and bot detection solutions. So just a quick introduction. My name is Mayank. I'm a security engineer at Dropbox. Currently, I'm working on intrusion detection. Before Dropbox, I worked at a startup called Stealth Security, where I was working on bot detection and abuse detection in general. Before that, I was a grad student at UC San Diego. So just a quick disclaimer. Most of this work was actually done at my previous company at Stealth Security, and also basically in my free time, basically over the weekends. Also, Dropbox is hiring. So if you're interested in abuse detection, please come talk to me after my talk. Okay, so let's talk about the problem statement itself. So bot detection. This is a pretty hot topic these days. This is a pretty big problem. Bot detection, essentially what it means is you're trying to defend against bots which are trying to automate some sort of an abusive activity. So this could be, for example, automated creation of accounts, for example. So these are fake accounts which you see all the time on social media. This could be automatically posting fake content. This could be, for example, scraping. So you have bots which are trying to scrape sites like, for example, LinkedIn. These could be bots which are, for example, testing out credential dumps. So they are essentially trying to test if the users on your site are still reusing the same passwords which are leaked in the credential dump. So essentially the problem is, is this activity from a human or a bot? The other problem is fraud detection. Somewhat similar. Essentially where what you're looking for is you're looking for anomalies in activities here as well. But here what you're usually looking for is anomalies given past behavior. For example, here, a common example is credit card transactions. So here you're essentially looking for, is this new credit card transaction does this fall in the same category of behavior given past transactions and so forth. Another category is manual account takeovers. So here, again, you're looking for anomalies given past historical data. And in bot detection, you're looking for anomalies given an entire population of data, if you want to think about it in these terms. Okay, so we introduce these problems, and of course, these are pretty big problems. Fraud detection, I would say, is pretty old problem, like credit card transactions. People have spent decades working on this problem. Bot detection is extremely huge, especially in the current world, given current political climate. So yeah, people have literally poured millions and millions of dollars just trying to solve these problems. So there are a bunch of in-house solutions, and there are also vendor solutions which are available to try to solve these problems, but people haven't really thought about how these solutions actually work, what they are trying to do, how they're trying to solve the problem, and are they really solving this problem? Okay, so in this talk, what I will do is I will start off with an example architecture. So this is, think of it as a common architectural pattern for any fraud or bot detection solution. Most of them follow somewhat similar patterns of architecture. And then given this example architecture, I'll talk about security issues with this sort of deployment. I'll also talk about some war stories from real-world deployments of some of these vendors as well. So let's start with the first, most common architectural deployment. This is the usual cloud-based deployment. So in this slide, in this case, you have your web server on the right-hand side. So the web server is basically serving all the content. And then you have the client browser on the left-hand side, which is basically requesting this content. And then you have some sort of magical service provider in the cloud. So this is your typical fraud or bot detection solution. So the flow is as follows. So the first step is the web request. So the client browser makes a web request to the web server. So for example, give me the login page. I want to authenticate to your website. And then the web server responds back with the page itself. So the interesting piece here is this file called fingerprint.js file. which is deployed somewhere in the service provider, say like abccdn.com or like somewhere, which is encoded within the page itself. So when you get back the page loads in your browser, this code automatically runs in your browser. And then this fingerprint.js file collects some sort of a fingerprint for your browser, for you. I'll talk a lot more about this magical file later on. But essentially what you're doing is you're collecting some sort of signals from the browser, like who is this user, like how is this user interacting with the web page, and so forth. And this fingerprint is, like in the third step, sent back to the service provider. So this happens like when you are basically interacting with the page, while you're interacting with the page. The service provider, again, has some sort of magical machine learning where they basically get these signals back, and they analyze them, and they get back some sort of a risk score or whatever their prediction is about this particular activity. Like, is this browser actually a real browser? Is this activity, does it actually belong to an actual human being? So the service provider calculates some sort of risk score. The next step is, the fourth step is the form submission. So this essentially doesn't even have to be a form submission. Think of it as some sort of a state change, which can cause some sort of an abusive activity. So in our example of authentication, the form submission is basically you're trying to brute force, for example, the authentication page. So during the form submission, the web server now gets back the contents, and then the web server basically queries the service provider, which is the fifth step, is tell me more about this request. What do you know about this browser? What do you know about this user? Can you tell me anything, like what is your prediction score? Should I allow this user in? Should I allow this activity, or should I not, right? So the service provider responds back with the risk score it had calculated earlier. And then there is this final piece, which is the mitigator, which basically, based on this risk score and other computations, it either allows the request to go through, so the activity, you can do the activity, or it takes some sort of mitigative action. For example, it can block the request, it can rate limit it, it can throw some sort of a CAPTCHA. You might have seen some of these CAPTCHAs also. So yeah, this is like an overall architecture where basically the service provider is sending some magical piece of code in your browser, which collects some fingerprints or some signals, and some machine learning model trains on it and then gets back a risk score. And based on the risk score, you decide, do I want to allow this activity or not? Another variant of this sort of deployment model is an inline deployment model, where instead of the service provider being somewhere else, the service provider is inline. This probably is more common with if you're using probably your CDN, and then you're deploying something in the CDN. So here, things are slightly simpler, where basically the inline device magically injects this fingerprint.js file directly into the page itself. So you basically don't have to even modify the source code of your application. And then the inline device also acts as the mitigator, essentially. Cool. So given this like deployment model, let's talk about the attacker goals. The attacker goals are pretty straightforward. Like if I want to, basically if I'm an attacker and I want to conduct some sort of fraudulent activity, I just want to do that without basically being caught by the fraud detection solution. Or if I'm trying to automate some sort of an abusive activity, for example, creation of fake accounts or posting of content, I basically want to automate that using some sort of a script without getting caught. Like, pretty straightforward. And then, of course, these solutions are trying to protect against that. And then the threat model here is, so what are the capabilities of this attacker? So in this model, that attacker basically controls the client side. So they basically control the entire browser. So they can basically craft requests to the web server. They can modify the responses, whatever you need. So essentially, like if you go back to the deployment diagram, they basically control the left-hand side, the client browser. Okay, given this threat model, now like we have established the architecture, we have established the attacker goals, we have established like the threat model. Let's talk about the security issues with this sort of architecture. The biggest problem here is you're sending basically JavaScript code to the browser, and there is basically no client-side attestation. there is no underlying primitive you can fall back to make sure that the code which you're sending is actually running. And essentially, you're sending this code in an attacker-controlled environment. So let's see like what are the issues which arise from this. So the first problem is the attacker can basically reverse engineer the entire sensor. So you're sending this magical fingerprint.js file as a response to every single web request. So if I'm an attacker and I make a request, I get back this fingerprint.js file. And this file is where all the magic happens, where you collect all the signals for your machine learning model, or most of the signals for your machine learning model. So I, as an attacker, I can open it up and see exactly like what I can open it up and see exactly what you're looking for. So let's talk about what they're looking for. So the first big piece is browser fingerprinting. So essentially, with browser fingerprinting, the idea is that you want to query the JavaScript process, and you want to ask questions about basically the browser or the operating system or the hardware. So this is a screenshot from the site called panopticlick.eff.org, where basically you can go to the site and then you can test your browser, and it will give you back your browser fingerprint. So this is the browser fingerprint of like my Chrome browser, for example. And you have the list of browser characteristics you're trying to fingerprint on the left-hand side. For example, you have system fonts. So here, what you're looking for is you're looking for the set of fonts installed on your operating system, right? On the right-hand side, you have the values. So these are all the fonts which are installed on my system. And the third interesting piece is the third column here, which is 1 in X browsers have this value. So 1 in 20.93 browsers, or almost 21 browsers, have exactly the same set of system fonts as my browser. So essentially, like if I was some sort of a data scientist and I was looking at this data set of all browser fingerprints for all web requests, just by looking at system fonts, I essentially cut down the data by 21, right? So essentially what you're trying to do is you're trying to query for these browser characteristics, and you're looking for characteristics which make your browser semi-unique. And you want to aggregate these signals to basically predict, for example, is this a real browser? Is this not a real browser? Or how common is this browser for this set of user? Like just to get into a little bit more details, browser fingerprinting, this is actually a pretty old technology. Here are a list of things which people are looking for. Things like any sorts of, as I already mentioned, fonts installed, plugins, codecs, language packs, anything which you install on your system which can make you semi-unique is pretty interesting to them. They're looking, for example, information about your display, the screen size, and so forth. Simple stuff like operating system version, user agent string. Another interesting piece is the hardware information. So here you're trying to fingerprint the underlying hardware from JavaScript itself. Like the first piece is the CPU architecture. So that's pretty straightforward. You want to ask, for example, how many cores are there in this processor. The next piece is GPU canvas fingerprinting, which is pretty interesting. So this came out a few years ago from a research paper, I think from UCSD, where the technique is what you do is you basically create some sort of an HTML5 canvas element, and then you draw some random image on top of this canvas element. And then what you do is you try to read the raw pixels back from this canvas element. And the problem is that due to differences in the actual GPU hardware, and also because of the device drivers, when you read back the pixels are fingerprintable based on the actual hardware and the device driver itself, which is very interesting, right? So you basically draw something on a canvas and you read back, and then the pixels are semi-unique. And this is also really cool because this is also really stable. So it doesn't really change over time because your GPU doesn't change over time, and then your drivers rarely update. Another interesting one is audio stack fingerprinting, where you're essentially trying to fingerprint. You're doing the same thing with the audio stack itself, with the sound card and the audio drivers. And one interesting tidbit here is this was introduced 1 year ago, around last year, by a paper from Princeton. And then as soon as they published the paper, within a month, Some vendors had basically implemented the same or similar functionality, which is pretty interesting, which means that they're looking for as much information as possible. So another scary part is none of this requires any permissions, right? It's JavaScript code. You can read like whatever you want. Another interesting stuff I found was people doing weird floating point calculations. So they would send down like weird mathematical problems, and they were looking for solutions like, did this code actually run? Did actually get a solution for this mathematical problem? Or they were doing weird manipulations to the DOM, create some sort of a fake item in the DOM, insert it in the DOM, remove it, and so forth. The other interesting piece here is user tracking. Also for this, for user tracking, you don't need any permissions. Here, like this is pretty scary stuff. Not everyone does this. Almost everyone does browser fingerprinting. Not everyone does user tracking. But with user tracking, what you're essentially doing is you're hooking for event types in JavaScript. And the event types are related to interesting stuff like mouse movements, key presses. If you're using a browser on a mobile device, like what is the device orientation? Did you change the device orientation? And essentially what you're looking for is you hook and you establish callbacks. So whenever an event happens, you get the event type, and then you get the timestamp. And what you're essentially doing is you're creating this vector of these tuples of event type and timestamp, which you can basically check on the server side. So essentially what you would get is, oh, at the beginning of the page load, the user's mouse was at this coordinate. Then slowly they moved the mouse to this coordinate. Then they clicked it. Then they started typing. And they press these keys. And then essentially, basically, you have the entire kind of session. And then you can recreate it on server side. And another cool but scary stuff is then you can also start fingerprinting the user pretty carefully. Like, what is their typing behavior? How fast do they type? How do they usually move their mouse? And so forth. Yeah, and then again, like this is pretty scary stuff. You don't need any permissions for this, and yeah, some vendors are definitely doing this. So yeah, you have the browser fingerprinting piece, and then you have the user tracking piece. The next piece is anti-tampering. So these solutions, these vendors or in-house solutions, they know that they're serving this JavaScript with every single web request. So they know that attackers are looking at this code. So what can they do? So they're basically they're implementing some anti-tampering technologies. I've seen like obfuscation being implemented. Basically, there is an entire spectrum where some vendors don't really care at all, and other vendors basically implementing really heavily obfuscated code. I've also seen like malware, like packed code, where you would send down some JavaScript which is really packed, and then you have an unpacking stub which basically unpacks the JavaScript and runs it. Pretty interesting. Another interesting implementation I've seen from like one particular vendor is they're randomizing the location of the JavaScript file itself. So you're loading this file from like some sort of service provider. Every time you load the page, the source code of the page would change, and it would point to a different file location, which was interesting. And some vendors have gone even one step forward, where every single time you load the page, this JavaScript code changes dynamically, which is interesting. But yeah, you want to run this code, but yeah, there's not much you can do. So the final piece is the payload itself. So you ran all this stuff, right? You collected the browser fingerprint, you collected the user behavior. Now you want to ship it back to the service provider. Like that's the payload. And I've seen different implementations. Base64 is very common. So you basically create a giant blob, and then you base64 encode it, and you send it back. Some vendors were using symmetric encryption. I don't even know why you would even try that. Like one vendor was using DES, and then the key for DES was in the source code. So like, I don't know why. Some other vendors were actually implementing their own custom encryption schemes. So they would come up with some weird function to encrypt the blob, right? The problem here is if I'm an attacker, I actually don't even care about the decryption algorithm. I only care about the encryption algorithm. And then I can basically rip out the encryption algorithm from the JavaScript and implement it in my own scripts, right? So yeah. Basically, there's no client-side attestation, so people are trying various levels of stuff. But yeah, none of this actually works. Next problem is there are actually no guarantees of correct execution of JavaScript. So first problem was you were sending this code to all the attackers, so the attacker knows what you're looking for. The next problem is this code actually doesn't even have to execute correctly. So I would say that the dumbest attack here was the stripping attack, where what you do is you actually don't even load the JavaScript. And then you, of course, never send the fingerprint back. And then the risk score is never calculated. So when the web server basically asks for the risk score, it doesn't get anything back. And then the entire thing basically fails to open. I don't know why you would do that. Maybe they are in some sort of a trial mode. I don't know. But this has definitely happened. Other common problem is replay attacks. So I talked about this giant blob, this payload which you are sending back. Like here is an implementation for POC. In this case, fingerprint equals something, that's the payload. And then there's no token within the payload which is dynamic, right? So on server side, there are no checks on the freshness of the payload. So the problem is that if I can capture this in something like burp or some sort of man-in-the-middle proxy, I can write a script which basically sends this blob or modifies this blob and actually have to never load the page and have to never run the script at all, right? So replay attacks, big problem. Okay, some people have tried to solve this problem with dynamic tokens. Like one specific vendor, what they do is they create a dynamic token to look for freshness of the payload. And then this token is generated from the timestamp. So there is a function f which takes in the input, the current timestamp, and generates a token. And then when they are sending the payload, they append this token, say t dash, at the beginning of the payload, and at the end of the payload, they append the timestamp. So on server side, they take out the timestamp, they apply the same function f, and match it with t dash, which again, you can replicate the same thing on your side as well, right? It is not providing any sort of value. Yeah. Other problems, yeah. Headless browsers. So headless browsers, something like Selenium, people use it for testing all the time. Phantom.js is also pretty common. Some of these vendors are aware of this. A few of these vendors are aware of this. They are also checking for presence of Selenium or Phantom.js. They're checking for presence of Selenium and Phantom.js in JavaScript, which again, yeah, goes back to the same problem. Okay, now in certain cases, the JavaScript is heavily obfuscated. So every single time you're sending this code, it's really hard to like reverse engineer it. So in that case, it's pretty hard to basically write a script and then automate everything. The problem there is the script, even though it's gathering all these fingerprints, there are still no guarantees of the legitimacy of these fingerprints. So what I mean by that is you can actually forge these browser fingerprints. So this is a paper which came out probably, I think, last year from INRIA, from France. This is a paper called FP Random, where they basically modified a browser, which introduces some sort of a noise in your browser fingerprint. So every time you visit a page, the fingerprint slightly changes. And then the reason they implemented this was for privacy reasons, because of course you can use all the same technology for user tracking as well. The thing is that you can basically reuse the same technology for helping to bypass some of these solutions. So what you can essentially do is you can come up with a database of normal fingerprints, which you can easily do if you have any normal site and you have any traffic. You can basically capture browser fingerprints on normal people, and then you can basically use some variant of this tool. So when I started working on this project, I don't think this paper had actually come out. So here is a reference implementation of this function called getCanvasFingerprint. So this is the function which is doing canvas fingerprinting, and this is from an open source library called fingerprint.js2. So just a quick recap, you basically draw something on a canvas and you read it back, and then based on your device drivers and hardware configuration, things are different, right? So when you call this function, you get some sort of base64 encoded string. Canvas fingerprint is something blah, right? That's the base64 version of the raw pixels. This is a normal browser. This is a browser I compiled from source. So this is WebKit, where basically I modified in the source code the function where you read back the raw pixels from the canvas element. So here, when you essentially call get canvas fingerprint, you get some sort of a fake canvas fingerprint, something which I control, which basically goes back to the point that since nothing on client side is trusted, even though you are doing heavily obfuscated code, you still cannot trust the browser itself because the browser will lie to you. And this actually happens in real world as well. So this is a tool which I found, which sells for $400 in the underground. It's called Anti-Detect. Brian Krebs wrote an article about it a few years ago, actually. This is a modified portable Firefox, where you essentially provided the fingerprint you want, right? You configure it, and then you run the tool, and then if any fingerprinting file runs, it basically gets back the fingerprint which you want it to believe. Pretty interesting. Clearly, the bad guys are not reading academic papers. Otherwise, they would use something like this, which is open source and free. OK, the next big problem is JavaScript cannot protect all flows. So we talked about on client side, there's no client side attestation on web. But usually you have, like, if you're talking about authentication, you don't only have the website, you also have some sort of a mobile app to access your service. And of course, for mobile app, you cannot depend on the service because, of course, you don't have JavaScript. So essentially, like, how do you solve this problem for mobile? One of the interesting solution here is you basically re-implement the same architecture, where instead of fingerprint.js, a JavaScript file, you basically create some sort of an SDK. You recompile the mobile app with the SDK. Instead of gathering browser fingerprint, you gather the device fingerprint. And then, of course, you send back the device fingerprint. You do the same computation again. And then, yeah, same thing. But the good thing here is on device side, there is device attestation. So for example, for Android, there is the safety net API. For iOS, there's this device check API. So essentially, what you can do is you can ask the operating system questions like, is this device rooted or not? Am I running on an emulator or not, right? So the app can ask these questions to the operating systems. The operating system can basically run a bunch of checks, gather a bunch of signals, and then the device attestation test is actually done on server side, again, not on client side. So things are definitely better. There are also like some work, for example, earlier this year, I think at Black Hat, there was some work about Android safety net and how it works and different issues. But yeah, we can basically assume that this works pretty well compared to the other model of web. So yeah, just to repeat, yeah, basically you have the mobile app SDK. You have, instead of JavaScript, you have some sort of native code, and then you're collecting device fingerprint. And then, yeah, let's talk about Android, for example. Like, why you want the device fingerprint? Again, you want as much signal as possible. I want to figure out exactly how the user is interacting with the device itself. And on Android, I started looking at some apps, and I started reverse engineering them. And the kind of stuff I found in some of the SDKs was basically crazy. So on Android, a lot of this stuff is available. Like, what is your IMEI number? What is your phone number? What is like information about your carrier, operating system version? I even found some vendors are trying to fingerprint your file system structure. What is your MAC address? What is your geolocation? List of installed apps, list of running apps. People are writing JNI code. On Android, it's basically, it's pretty bad. The situation is pretty bad. Of course, for some of the stuff, you require permissions, but for many of this stuff, you don't actually require permissions. And then I'm also not even sure, like, the companies which are using some of these vendors, do they even realize the amount of information these like companies are collecting? Because, of course, everything is sent back to their cloud for checking. So another thing to note here is on like mobile, the situation is pretty uneven. On web, almost everyone is doing browser fingerprint. There is already a pretty set standard of things you can do for browser fingerprinting, and almost everyone is doing the same thing. On mobile, things are really different. Some vendors are looking for something really basic, and other vendors are collecting a lot of information. Worth mentioning. Another problem is like, yeah, you have a mobile app for Android. What about iOS? iOS is a completely different beast. Since it's closed source, Apple has actually spent a lot of time trying to deal with this problem. You can only call a specific set of APIs for iOS, and then they actually have been deprecating some of these APIs in newer versions as well. So on iOS, things are definitely much better than Android. Still, you can collect some amount of information, but the amount of signal you can get on iOS is much less than on Android. Which brings to another problem. Like if I am an attacker and I know that on web you're collecting like 30 different signals, on Android you're collecting 50 different signals, but on iOS you're collecting only 10 different signals, I would like to pretend to be coming from an iOS device than an Android device or web, right? Okay. Then what about API? So even worse. So if there is also an API which you can hit for example, authentication or something else, API is supposed to be used by programs. And then with API, there's no JavaScript, there's no mobile app SDK, there's nothing, right? So essentially, you're back to things like rate limiting and then like IP-based stuff, basically fall back on this sort of calculations, which basically brings me to takeaways. So the first takeaway is there are found bunch of implementation and architectural issues in multiple deployments. Again, I think the fundamental problem is there is no client-side attestation. There's no root of trust in browsers. So people have tried, but you can still, of course, get some signal from browsers. So people have tried to solve this in multiple ways with anti-tampering, with obfuscation and stuff. But of course, since there is no base, this, of course, doesn't work, right? If you have read the Reflections on Trusting on Trust paper from like 1970, it goes back to that. The state of the world is better on mobile from a vendor perspective, that you can probably get more signal, and of course you have client-side attestation. But yeah, like for users, we have spent a lot of time and energy and research on browser fingerprinting, and people understand this as a privacy problem pretty well, but not many people have talked about device fingerprinting and the kind of stuff you can do while you can actually run code on the device, which is also a big problem. Another problem is getting a baseline protection across all flows is extremely hard. As I mentioned, that if you have web, mobile, and API, I will go after API. Why would I ever go after mobile, like after mobile Android, for example? So you're basically reduced down to the minimum set of signals you can collect on any flow. And of course, there are privacy issues with this because the same set of technology and the same set of signals can be used for basically tracking users. And actually, a lot of browser vendors are actually doing a lot of work against this. Like I think Tor has canvas fingerprinting detection. So if a script runs which is trying to access the canvas fingerprint, it basically has a pop-up and it shows you. And I think Safari has also done a lot of work here. And then also, I think with GDPR, like, I don't know, it's going to be harder and harder to collect these sort of signals. And yeah, just a final piece. Funny enough, these fraud/bot detection solutions are also fingerprintable. So they're trying to fingerprint the user, but you can also fingerprint the vendors themselves. Because, for example, a particular vendor, the script is deployed at abccdn.com/fingerprint.js. I know that now they are deployed here, like abccdn.com/fingerprint.js. Now I can scan Alexa top 1 million, all these sites. Let's look for all the places where you're loading this piece of code, right? So this is just an example. So I know all the places on the internet which is using the same piece of like bot detection or fraud detection technology. Suppose I want to attack a particular site A. This is the main target. I don't have to go after A first. I can go after another site Z, which is using the same solution. And I can learn like how do these solutions work. I can reverse engineer, for example, the rate limiting solution or whatever the rule-based systems are. And then I can go after A. So yeah, it's pretty funny that, yeah, they're doing fingerprinting, but they're also fingerprintable. Yeah, and that's the end of the talk. So if you have any questions.